So we talked about those double bonds breaking, and then we add new molecules, which would be like an H2 or an H2O onto it. Sometimes we don't know if a mixture contains a double bond or a triple bond. We just know that it's some mixture of organic molecules. So if we're trying to figure out what kind of mixture of organic molecules it is that we have, we can add it to bromine water. In bromine water, bromine itself is kind of a yellow-brown color to start with. So when we put a whole bunch of bromine into water, it's a nice solution, and that solution is going to be brownish. Now, if we're trying to figure out if a mixture that we have has alkanes, alkenes, alkynes, whatever the case may be, if we put this into the bromine water, a little sample of it, a little bit of bromine water, we get that yellowish brown turning to colorless. So it's just a test for us, just a way for us to identify what could potentially be in there. And then we've got a problem there. So we want the condensed structural formula for bromine addition reaction product of prop-1-ene. So we can write it out. Okay. Oops. Okay, I actually want to go back. Here we go. So I want you guys to talk me through this, either in the chat or you can unmute yourself as well. I want to hear some different voices, and if we can keep those videos on, that would be awesome, so I can see if you are doing well or not. And I know some of you can't because of tech things, so don't worry if you can't, but I like to see your faces. Okay, so starting out, bromine, what's the symbol for that?
Br.
Okay, I think I lost the sound of you guys. No. Let me see if I can fix that here. Awesome, thanks for typing in the chat in the meantime. And I could read some of your lips actually, that we've got BR, bromine, good. Let's see. Yeah, when it changed over, it changed. Go ahead and unmute yourself, say something, anybody.
Can you hear this?
I can hear it, yes, yeah. Thank you. Thank you, thank you. So we've got BR2, and thank you, Ilhan, for making sure that we know that we have to have that too, because it's diatomic when it's on its own. Excellent. And we have prop-1-ene. So again, I want to hear some voices, some new ones this time. So how many does prop mean? Heard a couple things, seeing a couple different hands. It is 3. C3. C3. Thank you guys for, if unable to mute, you were able to show me with your fingers. Thank you. C3, H6. C3H6. But it's easier for us in organic chemistry to draw it out, isn't it? So if I was trying to figure this all out, I would probably go with BR reacting with C double bond because of that one. C, C. We have H, H. This one, how many more hydrogens does this one need? Show me with your fingers or type it in the chat. This middle carbon. Yeah, just one. Thank you. Thank you for showing me with your fingers. And then we've got 3 at the end here. Okay. So when this comes in, breaks this bond, we now have a spot where we need to fill some stuff in because we have those hydrogens there, that one there, and those 2. But we need to put the bromines in to those missing spots. So Br, Br. Br, Br. So I know we can't do subscripts in the chat, but type in what would the condensed structural formula for this molecule be? And you can go ahead and type it in privately. What would the condensed structural formula be? Excellent question. So I had a question in here. Do we add both bromines or do we just add one? We've got to add both of them because this ended up when that broke needed one thing here and one thing there. And luckily we happen to have one of each of them. Good question. Thank you for typing that in the chat. Okay. Okay. So this is a good point because of a few of the questions I'm getting, a good point for us to review what that condensed structural formula is. So we always start with the carbons. And let's see, so many good answers. How about Lee, would you mind talking us through how to get the answer that you got? Just taking this and making it into a condensed structure.
Yeah, so so you start with the C and then I did H2.
Yeah, those two, good.
And then Br, which is right underneath.
Nice.
And then CH.
Awesome.
And then the second Br.
Excellent.
And then CH3.
Awesome. Thank you very much, Lee. And I wish we could have had your writing on here because your writing is amazing. If you guys haven't seen her writing before, you've got to get a sample of it because it's amazing. Awesome. And then we've got another question in the chat here. Oh, could the 2 BRs be next to each other or should they be on opposite parts of it? So again, we want to think, that's why drawing it out is really helpful. When we break that double bond, this carbon already has 2 hydrogens and that one single bond in between. Oops, I hit a button that made it go wonky, sorry. So it's got just one spot where we can put something. And this one had that hydrogen and a bond here and a bond here, but it's got one open spot. So we have to split them up over the 2 carbons. So it has to be on either side of the double bond. Great question.
Why does this H's come before the BRs?
Awesome. Doesn't need to. It's just the standard form that organic chemists tend to do. So they do the H's or the carbons first, followed by the hydrogens that are attached to it, followed by any other element that would be attached to it, like an oxygen or a bromine or chlorine or whatever it is. Great question, Zach. Thank you. Awesome. Awesome. And that was the same question that came in the chat from someone else. So perfect. Thank you, guys. Other questions on this one before we move on from addition reactions of alkenes? Thank you. So let's get back to the presentation here. Okay, polymerization. Oh my goodness, polymerization. What do you think polymerization is talking about?
Creating polymers?
Yeah, creating polymers. Polymers are like all over the place around us. Anything that's plasticky is a polymer, but also things like cotton. Cotton is a polymer that's made naturally. So cool. Okay, polymers are all around us, all over the place. And one way that they can form is through these addition reactions. It's not the only way, but it's one way that they can form. And it's just long chains of monomers that we join together in a reaction that just keeps going for a really long time. Kind of like that alkane reaction that we saw before. Can somebody type into the chat, or anybody can type into the chat what that alkane reaction type was called that went on for a whole bunch of different times? Yeah, nice. You guys are remembering different parts of it. Yeah, a free radical reaction. Beautiful, beautiful, beautiful. Where we're substituting, a substitution. Perfect. Good job remembering a few weeks back. So we can form long chains of monomers together, and they can either be formed naturally or artificially. So natural would be cotton. That's a good example of that one. Artificially would be like nylon. So two different fabric things there that we can think about. But again, polymers and plastics and all of those things are around us all over the place. So polymerization is the reaction that happens when we're forming polymers and sometimes occurs with an addition reaction. And we're going to look at the most simple one because often on IB exams, they've had where they've asked people to deduce what the product would be from some initial starting thing. And it's easiest to look at the ethene first to figure out what is going on. So if your video is up, show me with your fingers. If you are no video, you can type it into the chat privately or to everybody. How many does F mean? Awesome. Beautiful. I'm seeing it both places. Thank you guys. F means 2. So,
Wait, Miss Magdal, can you go back for a second?
Oh, yep. Sorry about that. Sorry. Oops, wrong one. Here we go. And back. Sorry about that. So we're going to make ethene become polyethene, or polyethene is another way that we name it. Through an addition reaction. Awesome. Give me a thumbs up if we're good now. Nice. Okay, thank you. Sorry for moving us too fast. And thank you for letting me know I was moving us too fast. Okay, we are going to get a clear canvas and starting out here. So you guys told me that carbon 2 and ene is what type of bond?
Double.
Yeah, double. Good. So we've got those two there. We've got hydrogen, 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 and hydrogen. So the first thing in an addition reaction, we're breaking that double bond. So it's going to be just a single bond. So we've got C, H, H, single bond, C, H, H. And we're going to have some radicals. So now these really want to react with something else. And if we're in the polymerization reaction, that means we're going to have a bunch of these CC, H, 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 double bonds that are breaking. So they're going to line themselves up along these spots where these radicals are going to be able to attach to one another. But we said polymers go on for a really long time, right? Really long time. I'm not going to want to keep writing these out. We'd be here for ages. So what we can do is first, let's bond these up together. So those two radicals bond, those two radicals bond. Oops, I forgot a radical on this side.
What we just make it a hexane?
It could be way more than that though. So what we're going to do is say, okay, these are going to keep going on, and we're going to put it in brackets. And even counting them would be insane, like counting a mole would be insane. So what we do is just put an N here to represent that it's a polymer that's going to go on for a really long time, but with an unknown amount of times. So we can't just count it. What questions do you have so far?
So you'd say that N is the length of like how many different radicals you have?
Yeah, yep, those radicals or those monomers is another word for it. That's how many, the N would represent how many, but we're not going to know exactly how many they are. So we just leave it at N. Great question. On Monday's asynchronous day, we are going to do a do now that's dealing with a more difficult one of these. And that'll be a good chance for us to see the kind that we might have to address at some point. So we will get back to that one on Monday. In the meantime, let's talk about another kind of reaction. Boop, boop. Oop. Hit the wrong one again, guys. Here we go. Okay. So alcohols, again, something that we would see do a combustion reaction. That's what we started with our do now. So we got that one out of the way. Hoo-hoo. But there are 3 different what we call classes of alcohols, and it's based on the number of carbon atoms that are attached to the carbon atom that has the OH group. Whew, that seems so cyclical. So we'll draw it out in a second. So we have primary alcohols, and those have just one carbon directly attached to the carbon that has the OH. Secondary has 2 carbons attached to the carbon that has the OH. And tertiary has 3 carbons attached to the carbon that has the OH. Whew. And I see just how I looked when I first heard this long ago, a little bit of puzzlement. What does this mean? So we're going to draw it out, make some sense of it. And we'll do it as a full snip here so you can keep writing the words. There we go. So if we have, let's change the color here. Okay, we're going to make this red because the important part of each of these is that OH being attached to a carbon. And then our second one, OH attached to a carbon, and OH attached to a carbon. OH, OH, OH. So in a primary, we imagine that this carbon is on the end of my molecule. So I have some other carbons. Remember, we represent R as some other stuff that's going off. And then an H. So this is imagining the end of the molecule. The end of the molecule. In our secondary, we have one hydrogen on it, but we've got an R group and an R group coming off the other sides. And we could do that R prime if we wanted to. So that's my secondary. My tertiary has 3 R groups coming off of it. So we don't have any hydrogens directly attached to that carbon. And we could do it again with the little primary and even the secondary symbol there too. So R prime, R double prime. We can do that if we want. So that's our tertiary. I'm hoping you're asking yourself right now, so, like, what does this matter, Mrs. Magdal? This, what, why? This doesn't make any sense. It tells us how reactions are going to occur when we have an alcohol. So if we have a primary, secondary, or tertiary, there's certain specific reactions that can occur with each. Which one do you think could probably form more reactions? The primary, the secondary, or the tertiary?
Primary.
Primary, any ideas why you would like to say primary?
Because the H's are a lot less electromagnetic, I think is the right word.
Yeah, electronegative, I think is what you're looking for. Yep. Yeah, they're less electronegative and they're taking up less space, right? There's just not a lot there. So we can do a lot more with it. Good prediction there. And we are getting so close to the end, guys. I don't want to stress us out. We have 5 minutes left and I have an exit ticket for you that I don't want us to miss out on. And I know I don't want it to be homework for you either because of all the stuff that you've got going on in your other classes. So I'm going to move us ahead here to our exit ticket. And we're just going to do the same thing we have in the past with them, which is just send me a picture of your work on it. And I'm going to actually, since we've got some time, I'm going to put you into some breakout rooms so you can work with other people on it.